Let us consider an example for TEE topology type network with number of stations 10 and using directional couplers with a splitting ratio 9:1. First, let us assume ideal couplers and connectors, so excess loss and connector loss is 0. In this case, total loss is the sum of n-1 times the throughput loss plus the tap loss. First, let us find those losses, throughput loss and tap loss. In order to find throughput loss, we need to have the ratio P2 to P1. How can we get it? So what we know is that we have an ideal coupler, no excess loss. So P1 equals P2 plus P3. And from the splitting ratio 9:1, we have P2 divided by P3 equals 9. From here, P1 equals P2, but instead of P3, we can plug in P2 divided by 9. Summing it up, we will have 10 over 9 P2, and solving it for P2 over P1, we have 0.9, which is not a wonder. For the directional coupler with a splitting ratio 9:1, 90% goes to the throughput port and 10% will go to the tap port. So P2 over P1 is 0.9. Plugging it in the expression for the throughput loss, we have minus 10 times log P2 divided by P1, that is times log of 0.9. Minus 10 times logarithm of 0.9 equals 0.46 decibel, and the ratio of P3 to P1 is 10% or 0.1. Plugging it into the expression for the tap loss, we have minus 10 times logarithm of P3 over P1, which is logarithm of 0.1. We have the tap loss of 10 dB. And therefore total loss is 10 minus 1 is 9. 9 times the throughput loss, which is 0.46 dB, plus 1 tap loss, which is 10 dB. Total is 14 dB. As a matter of fact, since we have tap loss 10 dB, sometimes this directional coupler is called 10 dB coupler. Remember, when the splitting ratio was 1:1, we have equal split between two channels, throughput and tap 50% each, and therefore, since we lose signal in each channel 2 times, the losses were 3 dB. That coupler was also called 3 dB coupler. But coupler in this example, where the tap loss is 10 dB, sometimes it's called 10 dB coupler. Anyway, continuing this exercise, let us now assume that we don't have an ideal directional couplers. Our coupler has excess loss 1 dB plus connector. For each connector will add 1 dB loss. We already calculated the ideal throughput loss for this directional coupler to be 0.46. So the real throughput coupler loss will be the ideal loss plus the excess loss. Since excess loss is 1 dB, we have 0.46 plus 1 equals 1.46 dB. This is the new throughput loss for real coupler. The tap loss we calculate the same way. The actual real tap loss is ideal tap loss plus the excess loss, which is 10 dB plus 1 dB equals 11 dB. Then total loss, we need to plug real throughput and tap losses plus add the connector loss, and in our formula that we derived in the previous lecture, we have to add 2 times number of terminals times the connector loss, because each terminal has 2 connectors, one on each side. Summing it up, we have 10 minus 1, 9 times 1.46 plus 11 for the tap loss, plus 2 times 10, total 20 for the connector loss, adding up to 44 dB. You see the difference? It is 30 dB difference. Without excess loss and connectors, in our example with ideal couplers on the previous slide, we had total loss 14 dB, and here we have 44 dB. So we have extra 30 dB, which is additional 1000 times signal attenuation. And this is a pretty large loss. So the system could be optimized better by choosing appropriate splitting ratio, but again, the choice will depend on the peculiarities of specific network deployment. This is all for this tutorial.